Now let's deal with activation energy. Now when we deal with activation energy, we deal with temperature also. So we saw how time and concentration make a difference for rate of reactions. Now we will see how temperature makes a difference, okay, for rate of reactions. So the first problem here, rate constant for a first order reaction, decomposition of a reaction A to B, Rk, and this is 4.75 times 10 to the negative 4 per second at 293 Kelvin, and K is 163 times 10 to the negative 3 per second at 303 Kelvin. So you can see that the K values are different. What is the activation energy of the reaction? So in this case, you gotta be careful, okay? Because if you're not careful with your ones and twos, then you might get wrong answer. Okay, so the equation for this one is K2 over K1, and you take the natural log of this, and this is equal to activation energy over R and 1 over T1 minus 1 over T2. Okay, that's your temperature change that's going on. And so for these ones, you really need to be careful about your ones and your twos. Okay, so our 1 is this one, K is 4.75 10 to the negative 4, and then K2 is going to be 1.63 times 10 to the negative 3, okay, at the temperature 2, which is 303 Kelvin. And make sure that temperature is in Kelvin, okay, always. It's much better because we are using R over here, and R is going to be in Kelvin, all right, for us. So here we are, Ln and K2 is 1.63 times 10 to the negative 3 per second, and K1 was the 4.75 times 10 to the negative 4 per second, which both of these are going to cross out. Activation energy is what we are calculating. R is the gas constant, which will be given to you, and this is going to be 8.3145 joules per mole per Kelvin, and we're going to convert this into kilojoules as well, because activation energy is calculated in kilojoules, so divide this by 1000 as well, all right? And then temperature 1 minus temperature 2, so 1 over 293 minus 1 over 303. You will see that your temperature doesn't usually come out to be negative, okay? So you have the smaller number here and larger number over here, okay? So when you subtract them, you should get a positive number. Okay, so then take the natural log of 1.63 times 10 to the negative 3 divided by 4.75. You do that on your calculator. You should get an answer of 1.233. If you don't get that, come and see me in class. And then EA is going to be, and do the calculation over here as well, times 120.3 times 1.13 times 10 to the negative 4. That's coming from the temperature, and this is coming from R value. And so then EA is 1.2333 divided by 120.3 times 1.13 times 10 to the negative 4, which is then equal to 91 kilojoules per mole. And the mole is coming from your R, okay, right here. Kelvin will get cancelled out because this is Kelvin here and that's Kelvin here, so that will get cancelled out, but you'll be left with kilojoules per mole. Okay, so that's your answer. Please check the calculations and make sure you get the same answers, or if you don't get the same answer, let me know if I did mine wrong. Okay, all right, let's do the next problem then. Decomposition of DTPB, whatever, doesn't matter, is first order. And you can see here that even first order, second order didn't really matter for us, okay? Because we're not calculating anything to do with time dependence or concentrations here, okay? So the K2 and K1, so the rate constants are given to us. or we'll be calculating those. So it doesn't really matter if it's first order or second order. With a half-life of 320 minutes at 135 degrees Celsius and 100 minutes at 145 degrees Celsius, calculate the activation energy for this reaction. So this is worded a little bit different, okay, and so which means that it requires a little bit more work, okay, than just doing a straightforward calculation. All right, so since the half-life is given to us, what we will have to do is calculate K first, because we are not given K. Okay, so K is equal to what? And so remember the T half-life for first order reaction, which over here it's going to matter to us because we need to calculate K. All right, so T half is 0.693 divided by K. Okay, and so we'll have to do that first. So let's get started. And so for K1, it's going to be 0.693 divided by 320 minutes, and this is equal to 2.17 times 10 to the negative 3 per minute. And then we'll calculate K2 the same way, so that's 0.693 divided by 100 minutes, and this is equal to 6.93 times 10 to the negative 3 per minute. Okay, so now we have our K1s and K2, and so we needed the first order reaction here in order for us to calculate the K value. Okay, otherwise we wouldn't really need it. We didn't need it in problem number 1. Okay, so once we have that, then we go ahead and calculate our temperatures, and we need to convert the temperature T1 135 plus 273, which is 408 Kelvin, and then temperature 2 is 145 plus 273, which is 418 Kelvin. Okay, so make sure that everything is in the correct units, and then all we need to do is plug it into our equation, which is the same as what we used before, which is K2 over K1 is equal to EA over R, and then 1 over T1 minus 1 over T2. Okay, so natural log of 6.93 10 to the negative 3 per minute divided by 2.17 times 10 to the negative 3 per minute is equal to EA, which we don't know, 8.314 joules per mole, again divided by 1,000 to make sure that we get into kilojoules, and then 1 over 408 minus 1 over 418. That's Kelvin, and our Kelvin is going to cross out over here. Okay, so 1.16 is equal to EA times 120.3 mole, kilojoule per mole, and then, mole per kilojoules, and then times 5.86 times 10 to the negative 5. Okay, and so then EA is going to be, and then you can divide 1.16 by all of this wonderful stuff and numbers, and you will come up with 165 kilojoules per mole. So the last part is the same as what we did before in the previous problem right here. The only change here was that we had to calculate the K1 and K2, okay, for us, because we were given only half-life, not given Ks.